Welcome to Lab 2 titled Line of Charges. The purpose of this lab is to conduct an experiment involving the interaction between two positive charged pieces of clear tape and determine the interaction. We also create a computation model of the electric field based on Newton's second law and Coulomb's law. This will be a model of distributed charge along the length of the tape. We will also create a more accurate charge for each individual tape compared to the point charge assumption from Lab 1. The findings for the lab is shown here, where the magnitude of electric force is 1.906 times 10 to the negative third power, and the line charge is 2.78 times 10 to the negative 8 coulombs. This is compared to the point charge of 1.48 times 10 to the negative coulombs from Lab 1. Newton's second law states that the net force of an object is the change of momentum over the change of time, where p equals momentum and t equals time. The gravitational force represents a force that pulls object towards Earth's surface, and that is represented by F equals negative m times g in the negative y direction, where g equals 9.8 meters per second squared, and m equals mass. Coulomb's law states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of the magnitudes of charges and inversely proportional to the square of distance between them, and is multiplied by the unit vector. The Coulomb's constant is the constant proportionality and is represented by 9 times 10 to the ninth power Newton meters squared over Coulomb squared. In class, we derived the formula for the electric field of a rod with a uniformly distributed charge that has a distance r from the midpoint. In this equation shown below, k is the Coulomb's constant, r is the position vector, and L represents the length of the object, or the rod. Q represents the charge, and r hat represents the unit vector. Assumptions for this lab is that the charge is evenly distributed along the tape. We can assume that each U-tip has the same net charge because the procedure for creating the tapes were the same, as the net force is 0. Here's the procedure for the lab. I create a U-tip by sticking one tape flat on my desk, taping another piece of folded tape on the base tape, and stiffly putting the tape on top from the base tape. I then observe the following interactions between a U-tip and another object, including my finger, another U-tape, and a charged plastic pen. Lastly, I suspended one U-tape on two objects of equal height, and then placed another U-tape underneath the suspended U-tape and observed the interaction, recording the separated distance between the two U-tapes. Here's a quick look at the free body diagram from Lab 1. As discussed before, because the electric force is equal to the gravitational force, the U-tape that is suspended must have a net force of 0. Here's a quick summary of the observations from Lab 1. We found the U-tip to be positively charged because the pen is negatively charged and both objects were attracted to each other. We also found the separated distance to be 0.031 meters. Here's the data I got from the experiment. I used the length and width of the tape to calculate the surface area of the piece of tape, and I calculated the number of atoms per tape by using surface area over the area of atoms. I recorded the separation distance with the magnitude of the wave vector r and the mass of tape piece by using this equation to get 0.0021 kilograms. Because we know that the gravitational force is equal to the electric force, I set the electric force equal to the mg, which is the gravitational force, and I set that equal to the external electric field times q. I then replaced the external electric field variable with the uniformly distributed charge for a rod, and then solved for Q, in which we got 2.78 times 10 to the negative 8 coulombs. This value will be used to estimate the charge of the tapes. Here's my code for the computational model. Here, the Coulomb constant and separation distance is listed, and the tape mass is listed as well. Then you see the line charge Q with the equation shown before to solve for it, and then you see the calculation of the E field, just like we did in Lab 0, in which we used the electric field equation. Next, we created a point charge along the line, making the model of the line charge, as shown below. Then we also created a model for the two tapes based on separation distance. Here's the second part of the code. In this section right here, we created a line of code that iterates through each of the point charges in the line charge to calculate all the electric fields so we can vector sum them and get the net electric field. In this part of the code, we created the arrows for the net electric force and the gravitational force. In this final part right here, we printed results by creating print statements. Here are the results from the line of code. Note the resemblance to the free body diagram a few slides back. Based on our results, the magnitude of the line charge on one piece of tape is 2.7 times 10 to the 8 coulombs, which is greater than the left point charge in Lab 1. For the suspended U-tip to float, the net force must be equal to 0 due to Newton's third law, for the gravitational force and electric force being equal to each other. And using the line charge in the model allowed for the electric force to be almost equivalent to the gravitational force, unlike with the point charge. The magnitude of the electric force ended up being 1.91 to the negative 3 coulombs. Possible errors is due to the lack of inconsistent tape and the handling of tape, which can be solved by using a neutral charge tape holder to hold tape A in place. Another issue is due to the mass of the pieces of tape not being exact, which can be solved by using a scale to measure the mass of the pieces of clear tape. Lastly, an error could have been due to the routing calculations, which can be solved by keeping calculations throughout the experiment. If I had modeled each of the tapes as a single point charge, we would have got the same result in lab 1, which is 1.48 times 10 to the negative 8 coulombs. But however, if we treated each point as a line charge, we would have got 2.78 times 10 to the negative 8 coulombs. The charge of a line charge model is greater than the point charge model by a factor of 1.3. These estimates differ because of the consideration of the charge being uniformly distributed across a rod-like surface instead of a point charge. Unlike the point charge model, the rod-like model considers the length of the rod and the rod distance from the observation point. The line charge model value is closer to the real value than the point charge value because there are many point charges added together through the law of superposition. The tape is more shaped like a rod than the point as well.